Hey friends, so in this video I will talk about decision problems in computing world. So a decision problem is a problem where you have to tell the answer in yes or no. For example, say you have to tell whether, you have to tell in a graph whether a certain node is reachable from a certain other node. If it is reachable, your answer would be yes, otherwise no. So these decision problems are categorized into different set of problems or classes. For example, P type of problem. P stands for polynomial, NP non-deterministic polynomial, NP hard, NP complete, right? So we'll go into details of each of those decision problem classes one by one. Let's go to P type of problems. So P-type of problems are the problem solution to which or solution to those problems is achievable in polynomial time. Now, what is polynomial time? Poly stands for many, though. So polynomial stands for, it's a mathematical terms and it stands for any formula in mathematics where it involves variables, coefficients, constant coefficients basically, and constant exponents. Usually the constant exponent size shouldn't be very large, otherwise the problem will become indeterminate, right? And then it won't be a P type of problem anymore. So usually like 50 is considered to be that number that if you got a polynomial type of problem and it got exponent, then if it is beyond 50 or say a number, a constant number k which is greater than size of the problem, then it is not a polynomial time solvable problem, or it is not a p type of problem, rather it's a np type of problem or other set of problem. So a p type of problem is solvable in polynomial time, so it's quite deterministic, and hence we call these type of problems are tractable, right? So here is my point that I was making earlier, that usually in worst cases the p type of problems are solvable in big O and k time, where k is a constant and n is the size of that problem. So usually this exponent, like when goes beyond 50, it becomes indeterminate. Well, let's go for an example. So this is a very simple example of mine, 5t plus x raised to power 5. Now, you could consider t as some other variable, which is like performing some work or some action, and x is another variable. So 5 is the coefficient here, multiplied by t plus x raised to 5. Now this is clearly a p type of problem, right? And let's take a look at a better example. Here we go. So it's a real-time example of what a p type of problem is. So we got a graph, right? And a problem statement is, do there exist any path to reach from P to F? So visibly, you could quickly say yes. Like from B, you will traverse to C. Now, from C, you will either traverse to D or directly to F. But whenever you reach to F, you will say yes, there is a path that exists in this graph that reaches from B to F. So answer is yes, and that is in polynomial time. Why I say it is in polynomial time? Because if you know the number of nodes, which is 5 here, and the vertices, you can easily determine that you would be able to give a definite answer, yes or no, by taking a look at all the combinations. So you know that it is solvable in polynomial time. Well, let's take a look at other example. So I'm giving you more examples here to, to give you a better understanding of what I mean by polynomial here and how polynomial problems are polynomial actually. So let's take a look at our second example. Let's read through the problem statement. So the problem statement is that in a graph which is above, for example, is it possible to color adjacent vertices with white and black colors such that no two adjacent vertices are of same color? So let's take a look at our example. So we got five nodes and these are the vertices A to B and A to C. Got two vertices, B to C, then B to D, and C to D, C to F, and D to F. Okay, so let's try to color those alternately, right? So A to B, if I say red, and A to C, if I say black, so those are alternate, right? Now B to D, well, B to C first. So I first colored A to B red and then A to C black. So B to C is going to be one of those colors. And as you see, these three are adjacent, right? So it's not possible. So answer is no. And I'm able to determine that in polynomial time. The graph can't be colored in this manner that your red and black are like color is alternating, right? So you will see that in this graph there would be at least one such adjacent set of vertices where you won't be able to provide alternate colors. Nevertheless, this was just a plain example of polynomial type of problems. Let's move on to NP class, NP type of problems. So NP stands for non-deterministic polynomial time solvable problems. So P type of problem was that you could solve that problem in polynomial time. NP type of problem is a problem that is hardly solvable in polynomial time. We wish that it is solvable in polynomial time, but it's not solvable in polynomial time. But it can be verified in polynomial time. That's called an NP problem. What could be a good example of an NP problem? Well, what about a cube root? So, think of a case where you are trying to find out cube root of some number. Well, programmatically, you have to either do an iteration from beginning till the half of the size, or probably one third of the size, or probably let's say till the till the number, right? And then you will actually keep on multiplying it three times with itself and see if it matches with the original number. And if it matches, that is your answer. That is the cube root. But if I say I give you two numbers where I ask you whether the number 1 is a cube root of number 2, like here in this example, 3 is a cube root of 27 or not, you would simply do this: 3 multiplied by 3 multiplied by 3, 3 3 9, 9 to 7, 27. You would say yes, it is. So you can see the difference, right? The, the solution is not polynomial, it is exponential. But whether the if I say whether this number is a cube root of 27, then you would be able to determine that in polynomial time. Such type of problems are called NP problems. Now, this is quite interesting. Well, it's not a class, but it's rather verses. And like people always wish to find a better solution of complex problems, better and faster solution of such complex problems. So that's where we actually will compare P and NP class. And there are like people who are looking in this direction that if it is possible to solve, not only verify, rather solve NP type of problems in polynomial time. If that would be done, that would be a dramatic change, and that would actually change the way we look at things. So most of us really don't believe that that there would be a possibility that P would be equal to NP. But again, there are certain people who are doing research around it and they think that P equal to NP is possible. So let's go one by one. Here, yeah. So a decision problem that could be verified as well as solved in polynomial time is called P equal to NP. So otherwise is called P not equal to NP, right? So usually like people are working on this and they are not able to find a solution to P equal to NP, but if one fine day they are able to, things would be different. A good example is like think of a case where you are like creating a crypto code basically, right? You are writing a crypto algorithm where you are able to generate some code which is like decodable, but it's very tough to decode that. But if you have to verify whether that code is a valid match, then you could verify that in polynomial time. But think of a case where you are able to solve that problem in polynomial time. That is, if you are able to determine the algorithm by that problem, or you are able to check whether a code is valid or not in a small time, then you would be able to break the crypto algo very easily, right? So that's another example of that. Let's move on. And yeah, so I talked about this like if there would be a possibility to solve NP problems or non-deterministic polynomial problems in a polynomial time, then most of the algos, sorry for the typo, and crypto would be crackable in polynomial time. Okay, next is NP completeness or NP complete class. So NP complete class is a subset of NP type of problem where this type of problem is convertible to other NP type of problem which is solvable, well, which is hard to solve, right? Uh, so think of it like, say, if I got a problem P, and if problem P is convertible to a problem L, which is solvable as an NP problem, then that's an NP complete problem. So, for example, let's go through the definition. I will just read it out so that it creates a basic understanding. So it's any NP hard problem which is transformable to a NP problem in a polynomial time such that the transform problem is solvable in NP is called NP complete. So for example, if I am given a set of integer and then if there exists any empty subset of them such that adds up to 0. Now this could be converted to n number of problems where you are given a set of integers and you have to just sum those up and see if any of like sum of any of such set is coming to be a zero. So you could actually determine all the subsets possible from this set of integers, and then those subsets could be like manipulated to check if the sum is zero or not, right? So this is a NP complete problem. Okay, NP hard. So NP hard type of problems are the problems basically which are not NP and are more harder to solve. But like its definition is like quite overlapping with NP complete. So usually like in mathematically we say that NP hard type of problems are a set of problems which are at least as hard as a NP complete problem is. Okay, so these are very hard to solve. That is quite understandable. So it's like from the complexity graph, it's like easier RP, then a little bit harder NP, then NP hard comes in picture. Well, NP complete as well, but like because those are convertible to other NP problem which are solvable in less time. Now, this example is same as the example I gave in NP complete class, right? So this is a NP hard as well, right? So this I got from Wiki. I has been going through Wiki and I found this, and this is quite interesting. And you can see that day we would be able to solve or say P equal to NP, and we would be able to, if we would be able to prove that, then NP hard would be the only category left. Otherwise, we would be having P equal to NP equal to NP complete. And like I said, the day we have P equal to NP, so we would be able to look at problems differently and solve those differently, right? Like our crypto, I don't know how that would work in future if P is equal to NP, but yeah, certainly that would be one area where we will need to work a lot probably, right? So here you can see that on the left side, NP hard got a good overlap with NP complete, right? So these are two sets, right? Where NP complete type of problems, we are saying like those are always NP hard type of problems, but those can be converted to NP, well, say lower down to or subdivided into multiple NP problems, which are solvable as a NP problem, or which are solvable in the time exponential, or you could say time greater than polynomial for simplicity. Alright, so that's it for this tutorial. So this was quite theoretical, though I tried my best to give you some examples as in where possible. So the important thing or important carry away is that you actually know these basics and you are able to categorize the problems to these different classes, and when you do that, you would be easily able to justify whether a problem is too complex or easier to solve, or it's like complex to solve but easy to verify. And this really helps. Such kind of identification really helps, though it have nothing to do with the problem solving ability of yours. But one thing you must have noticed is that P is always better than any other set of problem. If you are able to solve a problem in polynomial time, kudos, you are a champ. and you should always try to go for that, though we know that is not always possible. I i was just mentioning that p equal to np, the day that is done would be different approach of working that we have to devise, and we have to look back at things, and we have to look up for better solutions. Things like that will happen, right? So with that, I finish this tutorial, and thanks a lot, and please do subscribe. Thank you.